Alright, let's try example 2 in section 7.3. Very similar problem, just very slightly different. We do a little different substitution. We've got to integrate x squared dx divided by the square root of 9 minus x squared. And you'll see this is of the form the square root of a squared minus x squared. And that means we're going to use a substitution, that is x is equal to a times sine theta. In this case, a, of course, is 3 because a squared is 9, so you just have to take the square root of this 9 and we find out what a is. And we get a 3 sine theta. We want a dx because we're going to need that right there. And that's going to be equal to 3 cosine theta. Before we can fill out this form, though, we've got to kind of think about what this denominator is going to become. We know right now it's going to be the square root of 9 minus quantity 3 sine squared theta. And that, of course, we can multiply this out and we get something of the form 9 times 1 minus sine squared theta. Oh, actually, that's better. I hope you saw that mistake when I wrote it down, because that whole term is being squared, because this whole term is being squared, and this whole thing is x. Now we could make a substitution, trig substitution here, and get square root of 9 times cosine squared theta, because 1 minus sine squared theta is equal to cosine squared theta. And now we can take the square root of the 9 and the square root of the cosine squared theta, and we just get 3 cosine theta, and that's going to be our denominator. I guess technically we better put some absolute value brackets on that. Let's go back and take a look at this. Don't need 2 dx's, Cliff. And it now becomes x squared. But wait, now we don't want x squared here. We want 3 sine theta. So we get 3 sine theta squared. Dx is 3 cosine theta. And that's all divided by 3 cosine theta. And we see that these things cancel with these things. And we're going to get 3 times 3 is 9, so we get 9 on the outside. We don't need to leave it in there. And then a sine squared theta d theta. Now we've got to figure out how we're going to handle integrating that sine squared theta. And as you recall, in the last section, we spent a lot of time, with the power reduction idea and the double angle, and we're going to use that trick right now. So all we have to do is apply our memorized rule, and we can replace sine squared theta with 1 minus cosine of 2 theta divided by 2 d theta. And in this case, we can bring out our, we don't want to leave that in there, so we'll just bring it out and won't have to deal with it. And we could distribute it through here, and we get 9 halves integral of d theta minus 9 halves integral of cosine 2 theta d theta. And now this is going to be pretty easy to take our derivatives of. We get down here, integrals of, we get 9 halves times theta minus 9 halves times integral of 2 theta would be sine sine 2 theta divided by 2 plus c. And that's an intermediate answer for us, but of course we've got to get rid of our thetas and get back to x's. But we've got a little problem here. This sloppily written sine 2 theta. We don't have a way of substituting back in for sine of 2 theta. We have to deal with sines of theta. And so how are we going to get back? And to do that, we need to use another trig identity. It's amazing how often these trig identities come up. At the time we were memorizing them last semester, they didn't seem like much. But 2 theta is equal to, I don't know if you remember this one, 2 sine theta cosine theta, like that. So we can take this and substitute in, and we get 9/2. Maybe I'll just leave this out. Theta minus 2 sine theta cosine theta divided by 2 plus c. These twos will cancel, and now we're in a position where we can substitute back in x's for our thetas and our trig functions of theta.